Yeah, I'll be talking about this work soon. But before that, also, I'll also have to tell some stories about Spenta. And, so let me begin with the situation in which I was a student at Tata Institute. So I was a student during this period, and it was the time of the second string revolution. It was very exciting. I mean, all of us here, most of us at least, have seen this revolution, and it was very exciting for most of us, but it was very confusing for me, and it was even depressing, actually. And let me tell you the reason. It's in the next transcript. So the seminars in TIFR was all a buzz. You know, it was every day almost now and then. There were things like P-brains, D-brains, M-theory, F-theory, matrix theory. There were two of those, actually. And the ADS, and there's a slash, there's a CFT after that. I mean, and together with this nomenclature, we were supposed to digest the fact that all the strings are related, all the string theories are related. And as if you go to some schools, I mean, there were several schools I have gone to, and at that time people were saying, string theory is like a big elephant in which we are blind and we are given access to only a few parts of the elephant. So this was sort of the situation, and as a student, and of course this led to a huge amount of literature which appeared on the archive almost every day. It was called xxx.lanl listings at that time, I guess. And to an average graduate student, this is a horrible nightmare because you got to learn this quickly and you got to sort of contribute somehow. So it was a nightmare. And it was in this situation, actually, working with Spenta sort of helped me. So it was Spenta's advice was quite simple and easy to follow. Of course, I'll tell you a caveat in this soon. But this was what I extracted from interacting with him. So focus on first principles and a basic understanding of what you're doing. And the problem should be physically relevant. And you should find a good working model. I've highlighted that. A good working model for your quest. And extract the essential physics from the working model. And of course, this advice, as everybody, most of you will know, sounds like a reasonable advice, which any advisor would give. But Spenta did not give this directly to me. He did not explicitly say this. So he would give me snippets when you meet him. He would give me snippets about somehow Yukawa postulating the existence of a particle. And there is something about the material and which mediates the nuclear force. And about the Sakata model, which was the precursor of the quark model, and how there's an emphasis in materials in the method of discovering the laws of nature. And somehow all this is tied to Marxist philosophy. And so, but I mean, there's something about it. So now, if Spenta had given me directly, actually, I wouldn't have cared very much about the advice. But in fact, just about the caveat of the Marxist, there is in fact a theory, actually, which emphasizes some materialist realities. But since the advice was cryptic to follow, it made me curious. Okay. So I kept looking for guidelines in Spenta. And I learned the importance of working with obtaining a working model to discuss your physics, which I call material here, from the following paper during the time I was a student. And it was this paper, I think it was talked about, absorption versus decay of string theory in T-symmetry. And basically, it has a microscopic model of a black hole, and the description is valid at weak coupling, and the calculation demonstrates it behaves like a black hole. The classical absorption cross-section matches up to a proportionality constant and so on. And the word model, you can see the emphasis. Word model appears 26 times in this paper, in fact 9 times in the first with the abstract. So you can see the emphasis on the model here. And the detailed properties of studying the system essentially form my thesis. And till now, this model has continued to play a very important role in my physics. And I thank Spenta for introducing me to this very rich model. And in fact, there are problems still unsolved in this model. But working through this exciting times taught me how crucial it is to choose this important model. I mean, to choose a good working model for anything you want to attack. And what it does by doing this is eliminate the need to study too much literature, which was what was flooding the archive at that time. And it also enables us to study it independently, like with your own ideas. but you got to get the right model, and that, of course, is the essence of of being a good physicist. And I'm going to talk about how conformal invariance can be used to constrain spectral densities of conformal field theories at finite temperature. And it's appropriate to introduce this also by another work which I think I know he cherishes by my interactions with him. It's this paper on conformal invariance of string theory in compact space, which was also talked about, and basically discusses the role of role of this topological term for preserving conformal invariance. And this, as far as I know, is the first paper of string theory from India in the past, and it emphasizes the role of conformal invariance, which seemed to be crucial and in fashion even now. So let me introduce the work which I'm going to talk about. So what we're going to talk about is basically the sum rules of in a general conformal field theory in arbitrary dimension. And the sum rules we are interested in is basically an integral over the spectral function, okay, over the frequency domain. And this structure of the sum rules is such that when you integrate from -infinity to infinity of the spectral density, it reduces to expectation value of one-point functions. And this is the imaginary part of the retarded Green's function. And the sum rule actually is quite interesting. It relates two-point functions here to one-point functions, and you will see as we discuss, it has information of three-point functions. So it connects the first three, all the point functions together. And the sum rule actually results from analyticity of the two-point functions. You'll see that soon. So we want the Green's functions have to be analytic in the frequency plane, and it puts a constraint on the two-point functions, even though one does not know very much about the two-point functions. And these are useful in lattice calculation, where one-point functions are good to find, are easy to find, but two-point functions, in fact, the real-time retarded correlators are hard to do. And as we saw, it involves integral over the full frequency domain, and you will see that the right-hand side of the sum rule contains information of low frequency behavior, hydrodynamic behavior, as well as high frequency behavior. So it captures a lot about the theory, and we'll see how interesting it is anyway. And what we will do is focus on deriving sum rules for conformal field theories in arbitrary dimensions. And the operator we will focus on for the retarded Green's function is the stress tensor. And what we will look at is basically the retarded correlator of the shear channel of the stress tensor. And its Fourier transform is defined as follows. So let me just go through briefly the derivation. So as I said, the Green's function is analytic in the upper half plane of omega, and this comes basically due to causality. And there is another assumption for deriving the sum rule. Basically, it falls off sufficiently fast as omega goes in the upper half plane, as omega is large. And then by going through just simple analysis of Cauchy's theorem, you can actually obtain some rule of this kind. So I'm not going through this sequence of logic for getting this, but this is sort of the sum rule. So here is the imaginary part of the Green's function, and here is the Green's function evaluated at zero frequency. And this is an integral. And, but if you try to apply this to conformal field theory at finite temperature, and for simplicity, we will assume that there are no operators of dimension less than d in the expectation value, what you will see is that just by the operator product expansions, one can show that the Green's function actually diverges as omega to the power d. It just comes from a simple scaling rule, as I can just briefly allude to it later. It comes from a simple scaling rule. And then there is in fact even a finite term. And then there are terms which are suppressed after that. Okay? Therefore, the second assumption to obtain the sum rule in conformal field theories is violated. There's a diverging term, this is the red, and there is a finite term. So what do we do? So the diverging term is in fact identical to the one obtained by in the retarded Green's function if the theory is held at zero temperature. So what we can do is basically subtract the Green's function at finite temperature versus the Green's function at zero temperature. So that will remove, as we go to high frequency, because both behave the same way, that will remove the diverging part. To remove the constant term, just explicitly subtract it. Okay. So this is the constant term which occurs when you look at the Fourier transform of the Green's function, and you subtract it. And then in this function, this delta G has the requisite property to apply Cauchy's theorem and obtain the sample. And therefore, we apply the Cauchy's theorem and obtain the sample here. So what's on the right-hand side is basically this evaluated at 0 frequency. And on the left-hand side is basically the imaginary part of this difference. Okay? And one can show that this is real, so it doesn't contribute. And this is at 0 frequency. And since it's a 0 frequency, so it's basically this quantity evaluated at 0 frequency. This is finite, this is a constant term. And this at 0 frequency is basically the pressure. By hydrodynamics, this is pressure. And this at 0 temperature, the pressure vanishes, and that's 0. So it's basically pressure minus this finite term. So the first term is determined by hydrodynamics, while the second term is determined from the operator product expansion, that is high frequency behavior of the theory. So therefore, the sum rule is basically a constraint used by conformal invariance, because what I have used is the operator product expansion of the conformal field theory. So, but to proceed further and to get some information, at least for arbitrary conformal field theories in arbitrary dimensions, we need to go into a little bit more detail. Here is the paper which I will use. This is a paper by Osborne and Petku, who actually use conformal invariance and constrain the operator product expansion in arbitrary dimensions. This is, if people are familiar with 2 dimensions, which is what Spenta did used conformal invariance 2 dimensions for string propagation. This is a version of the OPE basically in higher dimensions, which is known for the stress tensor. And so this is the term which actually contributes to the divergence when you Fourier transform. And this is the term which contributes to the finite term. Now, and the coefficients, all these terms here, this is known explicitly. It's a horrible tensor structure, but it's known explicitly. And it's determined in terms of 3 parameters, A, B, C. And just to give some intuition of the 3 parameters, consider the 3 point, just to give an intuition of the 3 parameters. So it's a horrible tensor structure. In 2 dimensions, it's quite simple actually to write this, but in a higher dimension, it's quite complicated. And but just to give an intuition of this tensor structure, or the parameters controlling that tensor structure, basically what you have is the 3-point function of the stress. I'm focusing in D equals 4 just to illustrate the simplicity, to illustrate this tensor structure. The most general tensor structure in 3 dimensions from conformal invariance can be written in this following fashion. So you take any conformal field theory and evaluate this 3-point function. It can be broken down in this fashion. And it's basically composed of 3 tensor structures. And one, we can actually obtain it by taking a free scalar theory, which is like a model, a free scalar theory, and just computing Wick contractions. And, or a free vector theory. This is the second one, free vector theory, and using Wick contractions, and similarly, free parameters. So it can be parameterized this way. And this ABC, this is another independent way of parameterizing, is related linearly to this NS, NV, and NF in this particular fashion. And similarly, the central term is also related to ABC in some particular form. This is a formula for D equals 4, but a similar form structures exist in arbitrary dimensions. So once, if you go through the analysis, that's what we did, and perform this Fourier transform, you can see this expectation value in a thermal vacuum is basically energy. It's a diagonal, it's energy or pressure. And if you evaluate the finite term, it is of this structure. So I've written it in terms of this ABC and the dimension of the conformal field theory. So here it is. So it's of this structure, and this B is actually coming from a contact term in that expression of the tensor structure, the contact term, and it is necessary for to ensure conformal water integration. So there are two terms to it. One comes from a general tensor structure. One comes from a contact delta function kind of term here. And you have to do the Fourier transform. It's a little tedious, but it's straightforward to do the Fourier transform and obtain this result. So it looks a little complicated, but let's see what we can do with it. One of the things you can recognize, if you know a little bit of the literature, is that the first term we recognized to be actually something called the Hofman-Maldacena coefficient, which comes basically when you look at local excitations of a conformal field theory and look at energy profile. I won't go into very much detail because I have short time, but basically it's known as the Hofman-Maldacena coefficient, which can be read out. So the first term is basically that. And the second term is a contact term. And if you put them together and evaluate the right-hand side of the sum rule, you get an expression. Okay, you put them together, so this is pressure, and if you put all these together, you get some complicated expression. So this is an expression. And that's the sum rule. But right now, we don't have very much intuition about it. We just have the fact that, okay, we can find this term, and it depends on this parameters A, B, C, which parameterizes three-point function of the stress. Now, what we can do whenever we get a result, general result like this in conformal field theory, now, after ADS/CFT, what we can do is we can actually check. You can use holography to check this. And that's what we will do. So what we did was that this A, B, C coefficients have been obtained for a theory which admits gravity dual, meaning from ADS D+1, you can read out A, B, C. And it was done in the early days of ADS-CFT by these people. And these are the values. In fact, in their paper, it's a very cumbersome expression, but you can group them together, and it turns out to be this. Now, if you plug it back, this curly A and curly B turn out to be this, and okay, this is not so important, but the right-hand side of the sum rule collapses. It collapses to this very simple expression, d divided by 2d plus 1. So the sum rule for conformal field theory admitting gravity is quite simple. It's basically this expression, this d divided by 2d plus 1. And just as a check, this was using the explicit formula of the sum rule we derived, but we can derive the sum rule alternatively. So there's another method. It relies basically on evaluating the Green's function directly in ADS D+1 background. So the Green's function is supposed to be evaluated at finite temperature, which translates basically to evaluating the retarded correlator in a black hole background in ADS and obtaining high frequency behavior. And that can be translated mathematically. Basically, one has to study a differential equation, which is the minimally coupled scalar equation, and one can evaluate this. And it turns out to be this expression, going through the analysis. It turns out to be this expression, and you can convert using ADS-CFT what is the pressure, and it is certainly this expression. So it's basically, this thing serves as a check. So we have done this holographic check basically in two ways. We use the expression of ABC that we found, and the second way of directly evaluating Green's function at finite temperature, and therefore it provides a consistency check for the sum rule. And brief history, but maybe I can tell you the history later, but I'll just go ahead. So the sum rule we have got, and we have got a check on it, but still it's quite cumbersome. It's in this very weird parameters A, B, C, but there is a set of parameters introduced by Hofman and Maldacena, which are related to ABC by some linear relation, fractional linear relation like this, T2 and T4, and we can substitute them inside and see what the sum rule becomes. So it becomes this when you substitute inside, and you can see now, the gravity is at the origin in T2, T4 place. Basically, when T2 is equal to 0 and T4 is equal to 0, these terms drop, and it sort of, it reduces to the answer, which is Einstein's 2 derivative of gravity. And for d equals 3, there's some certainty all the time. This term is not important, and it's only one term which controls that thing. And in fact, one of the things I want to mention is that usually when you say a theory admits a 2 derivative gravity rule, there's a condition which is known, which is basically A hat equals C hat condition. And it can be seen that this condition of the sum rule is actually a linearly independent condition. And once you have the sum rule, in terms of this language of T2 and T4, you can use causality bounds found by these authors on T2 and T4. This basically confines the T2, T4 space to be some triangle, and gravity lies here. And using this bounds, you can translate. Basically, the sum rule is a linear function here, and the function is extremized at the vertices of this triangle, and you can find bounds on the sum rule. It sort of runs here between p by 2 and dp by 2, and for d equals 3, again, there's a special one, it's more confined. So, so what are the applications? So we just took the sum rule and tried to apply to the favorite theories we know, and what we obtain is the following. So for instance, in d equals 3, the favorite theories are I mean, basically, free theories of real bosons and Dirac fermions, and these values are known. They are sort of horrible looking. For instance, for M2 brane, they are sort of weird numbers like these. Again, if you plug them in the sum rule, it collapses. Therefore, for these theories, this value is not renormalized. Okay, free theory agrees with the strong coupling dual. Similarly, there is a theory called AB-GEM theory. It agrees, the weak coupling answer agrees with that of the gravity. And this is a very interesting theory, which people, many of the people here study. It's basically a theory where these values, ABC, are known as a function in 't Hooft coupling. And here is a function, theta is the 't Hooft coupling, and it's known as a function like this. And if you plug it inside, the sum rule reduces to this expression, and it lies within the predicted causality bounds. And in fact, it interpolates between free bosons and free fermions at theta is equal to 0 and theta equals pi. So therefore, yeah, and there is a very special point in which it becomes gravity. And similarly for the N equals 4 Yang-Mills, also the weak coupling answer agrees with that of the strong coupling answer. And we have also investigated other channels. This was the shear channel. And the other channels, though we didn't formulate it as a sum rule, what we can see is that if you take Fourier transform of that OPE coefficient, you can recast, it's basically controlled completely by something called the Hofman-Maldacena coefficient again. In fact, in the vector channel, it's the sum rule term itself together with the second Hofman-Maldacena coefficient here and some linear function. Similarly, in the sound channel also there is a very nice sort of truncation. It's basically again controlled by that particular Hofman-Maldacena coefficient. So let me just conclude, and I'm sort of almost up. Basically, we have derived a sum rule for arbitrary conformal field theories in arbitrary dimensions for a spectral function. And in fact, this is the sum rule. There is an assumption that no operator of dimension less than d acquires expected value, but we can correct this assumption, in fact, but the sum rule becomes a little complicated. It's not so elegant, but we can, in fact, correct it. And the causality constraints basically constrain the right-hand side of the sum rule to certain values of this. So it'll be interesting, of course, to investigate the other channels, especially holographically. And it's in fact interesting to examine in general what are the constraints conformal invariance imposes on spectral densities. In fact, in 2 dimensions, as you know, just the fact that by huge conformal invariance, you can actually find the because of periodicity, you can constrain the spectral density. In fact, you can obtain the retarded Green's function, but it's not clear in higher dimensions one can use that. So therefore, it's useful to see how much conformal invariance constrains the spectral density, and it might be rewarding to explore this direction further. So let me sort of end again with Spenta. During the last 10 years, when I sort of used to meet him now and then, he used to come here while building the ICTS, and he used to see me now and then in the Indian Institute of Science. And he used to complain to me. He used to say that he did not have time to think about the hard questions in physics that he loves. And these are sort of the hard questions whenever he talks to me about the conceptual questions about black hole physics and understanding thermalization. And perhaps now he will have time to contribute to these issues. And I wish him more momentous time.